welcome to week 3 lecture. So, in the last couple of weeks what we have studied is how we can execute an instruction, what are the various architectures that are existing, what are addressing modes, instruction format and various other things that are necessary for this particular course. Apart from that, we have used or we have said about a simulator, that is SPIM, and we have seen that how we can write programs using low level assembly language. In this particular week, we will be looking into how we can measure the performance of a CPU. We know that for any program you need some instructions to execute that particular program. Now, how you can actually measure the CPU performance? By that I mean that you can run the same program in two different CPU, and then how you can tell that which one is better. So, in this particular week we will be looking into the various aspects of CPU performance, and then we can say at the end of this week lecture that how can you say that my CPU is better than the other CPU. So, coming to the introduction, we know that most processors execute instructions in a synchronous manner using a clock that runs at a constant clock rate or frequency. So, what do we mean by that? By this, what we mean is processors execute some instruction that we have seen. Now, how that instruction get executed is through a clock. That means a clock is coming, and at the positive edge of the clock or within that clock period, we can say certain task is performed, and within a time period, depending on the frequency, the number of clocks comes in, that is clock is coming one by one by one. Now, what is clock cycle time? Clock cycle time is the reciprocal of clock rate, that is C is 1 by F. Clock cycle time is often termed as period, that is clock period, which is the reciprocal of your frequency, that is 1 by F. First, let us see these two factors, that is F and C, in some detail. Look at this. So, this is also a clock and this also a clock. Let us say this clock, this is the off period, this is the on period, and this whole is the one period. This is the off period, this is the on period. So, this is another period. So, this is one period, this is another period, this is another period, and so on. And let us say we have another clock whose period is little more. So, what we are doing here, this is the off period and this is the on period. So, this is the total clock period, sorry. Similarly, for this is the off period, this is the on period. So, this is your total clock, and so on. Now, you see that this particular clock, the time period is small, that is your clock cycle time is small, and in this clock the clock cycle time is more. And what we know that in some processor is performing a task with respect to these clocks. So, whenever this clock is coming, a particular task is getting performed. And so, what we can analyze from these two clocks? let us see that for the first clock, let us say the frequency is 1 gigahertz, okay, that is 10 to the power 9 hertz. So, what will be the time period? As I said, time period will be 1 by f. So, time period will be 1 by 10 to the power 9 second, that is 1 nanosecond. So, the period, this period is 1 nanosecond, and in 1 second the clock is going how many times? These many, 1 by 10 to the power 9 times, sorry, total is 10 to the power 9 hertz. So, the clock is on and off those many time period. Now, let us see about this particular clock. In this particular clock, the frequency is 500 megahertz. So, as it is 500 megahertz, then f is 500 into 10 to the power 6 hertz. So, what will be the time period? That is t equals to 1 by f. This will be 1 by 500 into 10 to the power 6 seconds, that is 2 nanoseconds. That means, for the previous clock, the time period is 1 nanosecond. For the next clock, for this one, the time period is 2 nanosecond. So, which will be faster? Obviously, the first one will be faster than the next one. So, now that we know that how we can relate clock frequency with clock period. So, both are related. Next, we see that on what factor does this clock rate depends on. So, there are two important factors on which this clock rate depends. The first one is the implementation technology. So, by implementation technology, what we mean is that with the advancement of technology, the size of this transistors are becoming smaller and smaller, and with that the clock speed is becoming faster. The clock is becoming faster basically. So, this is a factor where the clock frequency depends. Another is the CPU organization. What do you mean by CPU organization that we use? By CPU organization, what we mean is that, suppose in a clock period, we say that some part of the instruction is executed. So, basically an instruction is divided into some cycles. I mean, each of the work of that particular instruction is performed in those cycles. And by CPU organization, we mean how we can organize the CPU such that the number of tasks that can be performed within that clock period is maximized. So, in turn, we can say that for executing a particular program, we require some set of instructions. Now, to execute those instructions, we require some clock cycles, and ultimately if the clock period is lessened, then the total time required to execute that instruction will be even less. So, these are the two factors on which the clock rate actually depends. So, as I said just now that the machine instruction typically consists of number of elementary micro operations that vary in number and complexity depending on the instruction and the CPU organization used. So, by this what we mean that let us say we will take an example here. Add R1 comma R2. To execute this instruction, what we say that a machine instruction typically consists of number of elementary micro operations. So, to execute this particular instruction, we require certain steps 1, 2, 3 and so on. What are the steps? So, what we need to do first, this particular instruction is stored in memory. So, you have to bring that from the memory. So, first is the fetch phase. Once you fetch, how will you fetch it? The content of PC should be made available. So, using some operation, some control signals, we will make the content of PC available, that is PC out. We will see in details next, but in a simple word I will say that once we do this PC out, the content of PC is available to some bus, and then we have to put this value in MAR, memory address register. We know, we have discussed about all these register. Memory address register contains the address of an instruction or the data that is to be read from the memory. So, this we do PC out, MAR in, then we read, and then we do some other things. So, first we fetch the instruction. So, with just only these steps we cannot fetch, we may require some more steps to fetch. Now, what the point is, these particular steps can be performed, let us say, in one clock cycle, and there can be many more steps. Let us say to execute this machine instruction, what we require? We require some basic steps. Let us say we require 6 steps to execute this instruction, and we say that each of these steps require one clock cycle. So, this is what we meant by a machine instruction typically consists of number of elementary micro operations that vary in number and complexity depending on the instruction and the CPU organization used. Now, if you use a different CPU organization, these steps that I am saying might be different. Like say, for one type of organization, it requires 6 steps. For another type 2 organization, it may take 4 steps. So, we really cannot say that how you can differentiate. So, it depends on the organization used, and it depends on the complexity of the instruction as well. Now, moving on, as I said, a micro operation is an elementary hardware operation that can be carried out in one clock cycle. So, all the set of instruction, as I said, PC out, MAR in, read and so on, can be executed in one clock cycle. And in one clock cycle, what we can do basically is some register transfer instructions, some ALU operation instruction, because all those are within the CPU, and for that we do not have to bring it from the memory. So, whenever you have to bring it from the memory, that we have to see that how much time will be required for that. Inside the operation, transferring between CPU to CPU is much more faster compared to transferring or getting a data from memory to CPU. So, there can be register transfer operation, arithmetic logic operation. Thus, a single machine instruction may take one or more CPU cycles to complete. We can characterize an instruction by cycles per instructions. What do you mean by cycles per instructions? As I said, an instruction is divided into some basic operation. Some micro instructions are executed to execute that machine instruction, and all those machine instructions that all those micro instructions that are getting executed requires some cycles. So, ultimately an instruction takes certain amount of cycles to execute it. So, that is called cycles per instructions. So, every instruction is taking some cycles to execute, and that is termed as cycles per instruction. And what is this average CPI of a program? Average CPI of a program, as we can say that, see, there can be many instructions and many instructions can have different CPIs. So, average CPI of all instruction executed in a program on a given processor. So, we average it. That means, some instruction let us say takes 5 cycles, some instruction takes 7 cycles, some instruction takes 4 cycles. We average it out and then we say this is the average CPI, as different instructions can have different CPIs. We will see in detail. So, for a given program compiled to run on a specific machine, we define the following parameters. Okay? For a given program, now we are talking about a program that is compiled on a machine. These are the parameters that are important. What are the parameters? The total number of instructions executed, we call it instruction count. So, for a program, what is the total number of instruction that is executed, that is instruction count. The average number of cycles per instruction, as I have already discussed, that is the CPI. So, if there are 20 instructions and each requires some cycles, so cycles per instruction is the total average number of cycles per instruction. And finally, the clock cycle time or the period of the machine. So, now what will be the total execution time? So, the total execution time can be computed as, we call it XT, instruction count multiplied by number of cycles required per instruction and multiplied by the clock cycle time, or we can say the period. So, how do we evaluate and compare the performances of several machines? Next, we will see that. So, what is the execution time? So, now the execution time is the number of instructions multiplied by the CPI, cycles per instruction, multiplied by the instruction, multiplied by the clock period, or you can say the clock cycle time. So, you multiply all these things, you will get the execution time. We call it XT. Now, we will see how we evaluate and compare between the performance of several machines. So, one of the easiest method that can be used to compare is like, we measure the execution time of a program of two machines, that is A and B, and we say that execution time of A is XTA and execution time of B is XTB. So, what is the performance? Performance is 1 by X of XT of A and performance of B is 1 by, that means this is the computation time. So, let us say the one processor performs a task in 10 seconds and another processor performs the task in 2 seconds. Which one is better? The processor which performs a task faster, that means in less time, is better. So, the processor which performs in 2 seconds will be much better. So, that is why performance is 1 by X of TA, that is the reciprocal of this, or performance of B is 1 by XTB. Now, we can estimate the speed up of machine A over machine B as, speed up is performance of A divided by performance of B, and performance of A is 1 by XTA and performance of B is 1 by XTB. So, if you just put on these two values in this place, you will get the speed up of XTB divided by XTA, that is the speed up of machine A over machine B. Now, let us take some examples. Let us say a program is run on 3 different machines. So, you have A, B and C, and the execution times are 10, 25 and 75. So, what you can say from this? What we can say that A, that takes 10 is 2.5 times faster than B. So, B is taking 25. So, we divide 25 by 10 and we get 2.5. So, we can say that A is 2.5 times faster than B. Similarly, let us compare A and C, where we can say that A is 7.5. So, 75 divided by 10, we get 7.5 times. So, A is 7.5 times faster than C. And similarly, B is 3 times faster than C. So, B is 25. So, 75 divided by 25, we get 3. So, B is 3 times faster than C. Simple for one program, but what if you have different set of programs? How do we compare? This shall be discussed in course of time. Now, let us take an example. So, I say a program is running on a machine with the following parameters. So, what are the parameters? I give you the total number of instructions. So, what is your total number of instructions? This is your IC. Average CPI for the program. So, what is the average CPI? Taking into account of different CPIs for these 50 million instructions, we get a CPI of 2.7. And what is the CPU clock rate? So, we are giving you clock rate, that is frequency. So, from frequency you can find out the time period by C will be your 1 divided by 2 into 10 to the power 9. So, that comes down to 0.5 into 10 to the power minus 9 second. And as we know that the execution time is IC into CPI into C, and all those values are provided here. So, we get xt as this multiplied by this multiplied by clock period or clock cycle time, which is coming to 0.0675 second. Now, see what are the factors that affects performance. First one is the hardware technology. Definitely, if you make your clock cycle time smaller, then it is pretty obvious that you will be getting better result. But at the same time, you have to cope up with the operations that can be performed in one clock period or one clock cycle. Next is the hardware technology, that is the organization. So, what all factors that depends on this organization? First is the clock cycle time, another is the cycles per instruction. So, let us say when we talk about organization, it depends on how your various hardwares are actually mapped. So, depending on that, definitely your CPI, that is cycles per instruction, will vary. You have an efficient organization where your cycles per instruction can be reduced. So, this particular factor, that is hardware technology, that is organization, depends. These are the factors that will govern that is your CPI as well as your clock cycle time. Now, instruction set architecture, what all factors will depend? What is instruction set architecture? We have seen one of the ISA. So, instruction set architecture, by instruction set architecture we mean that how various kinds of instruction you are putting it in your architecture, how many types, how many varieties you are putting it there. So, definitely if you restrict the number of instruction to a minimum level for a program, you might require more number of instruction counts. But at the same time, if you say that you require, you have an instruction, you have more number of instruction, but those more number of instruction and to execute a program, that those instructions can be used. So, there are two things that can happen. Basically, what I am trying to mean is that, let us say you have add and multiply instruction, and in one case you only have add instruction. So, in this particular architecture, if you want to multiply two numbers, you can simply use mul R1 R2. But in the same case, if you want to use repeated addition, then you have to use a loop, and that loop will perform that addition number of times. So, this particular add instruction may be used in that loop repeatedly. So, the idea is, if you have more number of instruction, you might require less number of instruction in the end to execute a program. In a similar case, in this case you have less number of total instruction, but in that case you require more number of instruction to execute the same program. So, this is the difference by this. So, this instruction set architecture will, these two factors will depend. One is your CPI, cycles per instruction, another is instruction count, both will depend. Now, the compiler technology. Now, the different compilers can generate different codes. So, one compiler that generates some, let us say for the same program, one compiler is taking 10 instructions, another compiler is taking 20 instructions. So, this IC vary greatly on the compiler technology that is used. So, nowadays the compiler are becoming more and more intelligent, and they are going in hand with the hardware. So, the compiler must know what kind of hardware architecture you are using, such that it will generate the code in a fashion that will be easy for execution, and so such that it will also require less number of instructions. And of course, the program, that a program, what are the factors will depend? Both the CPI and the instruction count. So, as I discussed in the previous slide, IC depends on program used, the compiler and the instruction set architecture. CPI also depends on program used, compiler, the instruction set architecture, as well as the CPU organization. How you organize your CPU, how you organize your various hardware will also take this into account, the final CPI. So, final CPI will definitely depend on the CPU organization that you are using. And finally, the C depends entirely on the technology used to implement the CPU. And this is very unfortunate that it is very difficult to change one parameter in complete isolation from the others. So, the basic technologies are very much interrelated to each other. So, we really cannot vary one parameter completely compared to the other. So, what is the trade off here? If you see a RISC machine, the number of instructions per program is more. So, increases the number of instruction per program, but at the same time it decreases the CPI and the clock cycle time, because the instructions and hence the implementations are simple. But in CISC, decreases the number of instructions program, but increases the CPI and the clock cycle time, because many instructions are more complex. So, overall what has been found? It has been found that RISC architecture gives better performance. So, let me tell you with the same example that we have taken earlier. So, we have multiply instruction, and this is the instruction count, that is IC is 1 here, and for this let us say the instruction count, the loop executes 4 times. Okay. So, in such cases, depending on how many number, 4 multiplied 5 times with 5, or 4 multiplies 10 times. So, it depends on that. Now, IC is 1, but the number of cycles required to execute That means the micro operations that you are using, steps, in each steps we are performing something, that might be more. So, CPI, cycles per instruction, will be more. In this case, maybe IC is more, but the overall, let us say, it will take less number of cycles. So, CPI will be less here, but IC will be more. So, this is a trade off, we can say. So, for in one case we can have more IC where the CPI will be less. In some case we have less IC, that is instruction count, but the CPI in turn will be more. Let us take an example. Suppose that a machine A executes a program with an average CPI of 2.3. Consider another machine B with the same instruction set and a better compiler that executes the same program with 20% less instructions and with a CPI of 1.7 at 1.2 gigahertz. What should be the clock rate of A so that the two machines have the same performance? So, for both the machines, CPI is given and one machine executes the same program with 10% less instruction. So, one takes 100% and another takes 20% less, so that means 80%. So, for A, ICA will remain same, this is 2.3 and this is CA, that is what we have to find it out, clock of A. And for this, IC is 20% less, so it will become 80%, so 0.80 into IC into 1.7 into this is the clock rate, this is the period. So, the clock rate is 1.2 gigahertz, that is 1.2 into 10 to the power 9, 1 divided by that will give you the clock period of this. You just solve this, you will get a clock period of 0.49 into 10 to the power minus 9 second, which is coming to 2.04 gigahertz. So, we need 2.04 gigahertz of clock for A, machine A, such that both the result should be same. Let us take another example where consider the earlier example with instruction count of 50 million, average CPI of 2.7 and clock rate of 2 gigahertz. Suppose we use a new compiler on the same program for which new IC is 40 million and the new CPI has also increased, which is 3. Also, we have a faster CPU implementation with clock rate of 2.4 gigahertz. So, these are the different. So, one is having 2 gigahertz, this is having 2.4, but the CPI of this is less, CPI of this is more, but the instruction count of this is even more and this is less. So, if you compare this, what will be the speed up? You have to find the execution time of old one compared to execution time of new. So, you just put those values, you get the execution time old, which is of this one, and you put all these values, you will get the execution time of this one. So, which is coming down to 1.35. So, we can say that it is 35% faster. Let us take another thing, which is instruction types and CPI. Consider a program executing on a processor with n types of classes of instruction. So, generally we do not have one kind of instruction, right? We have load store instruction, we have data transfer instruction within the CPU, we have variety of instructions basically. So, these classes are divided into, let us say, load, store, ALU, branch, etc. So, IC of I, that is number of instruction of type I executed, CPI is cycles per instruction of type I. The following expression follows from this. So, till now we were saying that this is the total IC, this is the total CPI. Now, we divide it. We say that there are various kinds of instructions. So, we can have various kinds of instruction and each of these instruction can have different CPIs. So, each instruction will have different CPI. So, CPU cycles, clock cycles will be instruction count of I into CPI of I, summation of that. Similarly, instruction count will be considering all the instruction of all the types, IC of type I, where I goes from 1 to n. So, there are n type of instructions. And what will be CPI now? CPI will be summation of instruction count and cycles per instruction divided by instruction count, total instruction count. So, summation of IC of I divided by IC into CPI. So, fraction, this is what fraction of instruction I, type I instruction executed. Let us take one more example of where we consider the implementation of an instruction set architecture where the instructions can be classified into 4 types basically. So, the CPI values of these 4 types instructions are 1, 2, 3 and 4 respectively. 2 code sequence have the following instruction count. That means, there are 2 code sequence and these are the various instruction count of type 1, instruction count of type 2 and so on. So, now you see the CPU cycles for CS1, 20 multiplied by 1 because type 1 the CPI is 1, type 2 multiplied by 2, so which is type 2 multiplied by 2, 15 multiplied by 2, 5 multiplied by 3 and 2 multiplied by 4. So, this will give you the total CPU cycles, that is 73. So, what will be the cycles per instruction? So, total instruction 20 plus 15 plus 5 plus 2, which is coming down to 42 total instructions. So, CPI will be CPU cycle divided by 42, which is coming down to 1.74. Similarly, for the next one, total CPU cycles is 80 and CPI is 2.22. So, we can see that it greatly depends on both the type of instruction and what is the CPI of that type of instruction. So, both varies. So, this is instruction frequency and CPI, where CPI can be expressed in terms of frequencies of various instruction types that are executed in a program. So, Fi denotes the frequency of execution of type I. So, Fi is IC of I divided by total instruction count, and CPI we have already shown it in the previous slide, can be expressed in terms of frequency. So, we substitute this here. So, we get frequency multiplied by CPI of I. Now, let us take another example where suppose for an implementation of a RISC RSA, there are 4 instruction types with their frequency of occurrence for a typical mix of programs, let us say, and CPI as shown in table below. So, this is the frequency at which load instruction is executed. This is the frequency at which store instruction is executed, and this is the frequency for ALU and branch. So, and the CPI is given, cycles per instruction. This is the frequency at which it is happening. So, what is the frequency? That is 0.2 and the CPI is 4. So, if you want to find CPI, you can find Fi multiplied by CPI of I. So, 20% 0.20 multiplied by 4, 8% 0.08 multiplied by 3 and so on, and we get 1.88. Let us take another example. Suppose that the program is running on a machine with the following instruction types, CPI values and frequency of occurrence. The CPU designer gives 2 options. The first option is to reduce the CPI instruction of type A to 1.1%. So, type A instruction we are reducing to 1.1% and reduce CPI instruction of type B to 1.5. So, CPI of type B is reduced to 1.6. So, this is type A is reduced from 1.3 to 1.1 and type B is reduced from 2.2 to 1.6. Now, let us see. So, average CPI for A will be 60.5 60%, so 0.60 multiplied with 1.1, this is the new CPI, and all the rest CPI remains the same. So, we get 1.4448. Similarly, the CPI for B is 0.60 into, no change here, but here we change to 1.6, this 2.2 becomes 1.6 and this remains same. So, we get this. So, from this what we clearly can say is that option A is better. But you see what we have done. Option A is we have reduced from 1.3 to 1.1. But you see the frequency of this instruction that is getting executed, that is 60%. So, it is much more. So, you must take into account the frequency. So, some instruction which are frequently getting executed and you reduce the CPU even less amount, but you are using that particular instruction much more. So, in that case you will get a better result, even if you are reducing certain CPI to a great extent, but that is not executed more. So, you see that type B is executing only the frequency of execution is 10%. So, in that case if you reduce it to 1.6 also, you are not getting a better result compared to when you are reducing A to just 1.1. So, we came to the end of lecture 12, where we have seen that various things that affects the CPU performance, and next we will see in some more detail in the next lecture.